So, waves. We're going to start off looking at the properties of waves and how we can classify them into two different groups, transverse or longitudinal waves. Now, wave, typical wave that you can think of, water wave, a ripple on the surface of a lake. The ripple travels away from the object that's causing it. The object that's causing the wave tends to be something that is vibrating or moving, and the wave travels then away from the object. The actual ripples themselves are up and down movements, so the boat here will go up and down whilst the wave travels past the boat. So the vibration of the wave in this type of wave is up and down whilst the wave moves along the surface of the lake. So we can call the direction it's moving direction of travel, or the direction that the wave is transferring energy, and the vibration or the oscillation, the vibration of the wave is up and down. And in a transverse wave, this up and down, this vibration is perpendicular to the direction that the wave is travelling. So, best demo is a slinky. If we're moving our hand up and down to make waves on the slinky, and then the wave is travelling in this direction, then it's a transverse wave because the vibration up and down is perpendicular 90 degrees to the direction the wave is travelling, or at right angles. So, parts of the wave that we can identify and give them names. We call the top bit peaks, like the peak of a mountain, and the bottom bit here we call a trough, which is what a pig eats from. So this is a trough, this is the peak. Examples of transverse waves, waves on the surface of the water, and electromagnetic waves, which include light, but you've also got radio waves, microwaves, infrared, you've got ultraviolet, you've got X-rays, you've got gamma rays. All of these are electromagnetic waves. All of these are transverse. Okay, and if you really want to show off, S waves, the secondary waves produced by earthquakes, are transverse, which causes a side-to-side movement as the wave travels forwards. So, how do particles in a transverse wave move? Let's have a look. So the vibrations are up and down. So as the wave, I set it off, the wave is moving that way, to the right, and the actual vibration, actual physical movement of the particles is up and down. But note that none of the particles actually change position. They all stay in the same place. So the wave does not transfer matter, it transfers energy. So frequency is how many waves we have passing a point per second. Here I have more waves passing the mouse point there per second, and even more. Low frequency, I have fewer waves passing per second. Okay. So then we've also got the wavelength. So wavelength is the distance between two peaks. It's the same as the distance between two troughs, or you could measure from the middle, but the easiest thing is to identify peaks and peaks, troughs and troughs, and to use that distance. Measured in meters. Okay, so really it's the distance between two identical points on the wave. And we use a symbol lambda here, okay, Greek letter, for representing wavelength. And we use meters to measure. The amplitude of the wave is we say how high it is, but we need to remember that if there's no wave, the water or the substance the wave is travelling through, which is, we call it the medium, would be here on the x-axis. So the height of the wave is how high it's gone from the resting point if there was no wave, or how deep will be the same measurement. Okay, and you have to watch out, do not measure from the bottom of a trough to the top of a peak, because that is 2 times the amplitude, that's double the amplitude. Now, the bigger the amplitude, the more energy the wave is carrying. So, let's turn on the simulator, and for example, if I increase amplitude, the waves get taller, and the amplitude here will be 1, 2, 3 squares. 1, 2, 3 squares. 1, 2, 3, 4 squares, the amplitude. Wavelength would be the distance between 2 peaks. At the moment it's set at 1 square. Okay, if I pause, you can see distance there is 1 square. 2 squares, 3, 4 and 5. Now, if the frequency is how many waves are passing a point per second, so if we choose this line as a point, we would time 10 seconds for example, and count how many waves are passing in 10 seconds, and then divide 1 by the number of waves passing per second. So at the moment, 1, 2, 3, it's about 3 waves per, about 1 wave every second. If I increase the wavelength, that's less waves passing per second. Decrease the wavelength, and there's more waves passing per second. So decreasing the wavelength increases the frequency. So here we've got frequency. Number of waves passing a point per second, or unit of time. And we measure that in a unit called hertz. So 1 wave per second is a hertz. If all of these passed in 1 second, what is the frequency? Well, we've got 1, 2, 3, 4 complete waves here. So that's 4 waves passing in 1 second, so that'll be 4 hertz. Okay, so here we've got an activity to do which I'm going to put in Google Docs for you to complete the table. And that's the first part.